All right. The first thing that I wanted to talk about were, setup and hold time violations. Is this what 4B was kind of like? Was it this style? Okay, yeah, great. So, so this is very similar to a question that you received on one of your homeworks, and also similar to a question that you received on your midterm. I think this is a really great question that really tests your fundamental understanding of the sampling period and the timing apertures of flip-flops. So we're going to go through this, and we're going to determine if there are any violations in this. So this Q right here, this is the expected Q. This is if there were no violations, so if maybe the flip-flop was designed in a way that, there were no violations and this was the output, this would be correct. So the question now is if we have instead this set of parameters, then will this Q be correct, or will we have any timing violations? Okay, so take 15 seconds, maybe 20 seconds to kind of look at it. Okay, so we have a setup time of 1.5 nanoseconds and a hold time of 0 nanoseconds. So what will the width be of our aperture? We shout it out. 1.5, okay, great. So, and then it will probably be kind of around this region where our hold time is right here, but our setup time is 1.5 before, so it'll basically be this box right here, and then similar on the other pause edge as well. So if we change the value anywhere in this box, then that will likely mean that we have a hold time violation. But if we didn't even set up the correct value right before this box, that means that we have a setup time violation. So in this case, we were expecting that, and then also, so what is the clocked Q here? Looks like it's 1 nanosecond. Yeah, okay, so every box I'm considering is 1 single nanosecond. Yeah, so here it looks like we have a clock to Q of 1 nanosecond. Okay, but we can see that D is currently being sampled as a 1 for this entire region, and then Q is produced as a 1. So is there any timing violation here? No, it looks like we're good. Okay, but then over here, all right, so if we zoom in really close, it looks like D changes right before this pause edge. And so therefore, does this D change in the middle of this aperture? It does. So therefore, what violation is this? So it wasn't, so if we look at the setup time, so setup time is 1.5 nanoseconds. So that means at 1.5 nanoseconds before the clock edge, was this value what we were expecting? So we were expecting 0, and is it equal to 0? Yes, so therefore this is not a setup violation because it was set up correctly. But then, right before the pause edge, it changed, so it wasn't held for long enough. So this is a hold time violation. Setup time violation is just like this part of the box right here. That's setup. But hold time violation is like the whole width of the box. Okay. Let's say that instead of this, maybe we have, yeah. Okay, let's say that instead it continued for longer and then now went high. Is this a violation? No, because it was held past the whole time, so that's good. Okay, let's say now maybe this is kind of reversed a little bit, and now we have something like this, where just for a little bit it goes to 0. And so, but we were expecting it to be 0. we were expecting it to be 0, but then afterwards D is 1. So then what violation would this be? Yeah, this would be a setup violation, because if we look at just this first little bit right here, this first little bit, it is not set up correctly. It should be at 0, but instead it is not at 0. Yeah, question?
I was reading online when I was doing the homework, so they were saying that if you have no hold time, you can't have a hold time violation online. Is that not true?
In an engineering, like, oftentimes when you have a 0 nanosecond hold time, oftentimes it is very difficult to get hold time violations, but there are situations where you could have, like you could have this situation. All right, come on. Yeah, you can absolutely have this in real life. Like, you can have a D that like is supposed to be like valid, but because of clock skews and maybe the flip-flops aren't exactly all triggering at the exact same time, because of that, you can actually have things where your D arrives and you have a hold time violation because of all like the other clock skews and things. Yeah.
So even though it like happens inside of like the setup time window, it's still considered a hold.
So there's no setup time window. The setup time is just this instantaneous moment right here. That is just, are we set up to the correct value? Yeah, and I know some textbooks, some people, some resources probably give like the wrong like explanation of this. But like when you actually create real flip-flops and when you're characterizing flip-flops and when like if you go and like, create your own flip-flop and you are trying to calculate the setup and hold time, it becomes like very clear that there's like this very like this instantaneous moment here that is the setup time, and then anything past that, it's very clear that it requires like a whole different like kind of violation. It's a lot of resources online will say like there's a setup window. But those are generally written by people who actually haven't like built flip-flops. In Beanie.
Okay.
Yeah.
So for this example, because it is slightly before, like there's a change in that region. This is a hold time violation.
This is a hold time violation.
Okay, so what if we had like a hold time with like a set amount of time, like that was not 0?
Oh, well, if it was not 0, then our timing aperture would just be extended a little bit, because if our hold time is 1 nanosecond, then it would just extend out to here. And then, this would very clearly now be a hold time violation, because it very clearly is, it's like, it's not held for this entire time. Yeah?
So to pass it, or like to not have a violation, you have to have like a half a nanosecond of like negative hold time?
Exactly, right. Yeah, so in order to fix this, instead we would need to shorten this aperture to now, maybe something like this instead. All right. So now this would mean that now we have a half a nanosecond of hold time. And now, because of that, it was in this entire region, the correct value was held. So therefore, we have no hold time violation. And we have no setup time violation, because we were expecting it to be 0. And at this instantaneous moment, right here, we can see that that it was set up to the correct value of 0.
Yes, that's a negative hold time right now, right?
This is negative half a nanosecond hold time.
Okay. I remember earlier you said it's not possible to have like a hold time violation if it's negative hold time.
Oh, in this class. I was, so in this class, I am not talking about clock skew. But in future classes, you may now be introduced like another parameter that is like, now imagine that your flip-flops all trigger at slightly different times. And so now because of that, even though some flip-flops have negative hold time, you now can have hold time violations. In this question though, I very clearly am giving you the case where D arrives right before the pause edge. I'm showing you even though generally negative hold time fixes all hold time violations, In this case, we actually do see that there is, D arrives before the hold time is satisfied. Yeah.
So our timing aperture should always match the expected Q.
Say it again?
Our timing aperture should match expected Q, right?
Exactly, yeah. Right, so we can see, for this whole period, we should expect it to be held at 0. And that's because we're expecting Q to produce 0. Yeah?
So if we had a negative hold time, would the timing aperture look like that? And then in the D, if we had like a spike inside of the timing aperture that went up and then back down,
Yeah.
would that not be a hold time violation?
So you're saying if we got like a spike right here,
Yeah.
Yeah.
this would be a hold time violation. Yeah. Yeah. If we had a spike maybe right here, though, then this would still be fine. This would not be a violation because it is outside of this aperture. The most important thing is this sampling window, this aperture. If we ever change anything inside of this aperture, that is almost always a hold time violation. The only time it's not a hold time violation is if we were wrong from the start. If we were wrong from the start, then that's a setup time violation. Yeah?
If you were wrong at the start and you had a full-time violation, would it be both? Or?
I would just call that a setup violation. Yeah, so if you have something like this, and then maybe another spike later, yeah, I'd probably just call this a setup violation because at this moment, it's set up wrong, it's already wrong. Doesn't matter what happens after that, the value is going to be incorrect. I would just call this a setup violation. Yeah?
Is the red box, are you basing that off of the setup time?
Exactly, yeah. So the setup time denotes where the box starts, and then the hold time denotes where the box starts. But actually, this number is wrong because we are now doing it for 0.5 nanoseconds. Yeah, so, and it's negative 0.5 because that's how early, before this clock edge, that right there is 0.5. Yeah.
And then for D,
Uh-huh.
it has to remain 0 because Q is 1 for the setup time,
So on the next cycle, so on this next pause edge right here, on this next cycle, we're expecting Q to be 0. And because we're expecting Q to be 0 on the next cycle, that's why D needs to be 0 within the aperture. So it's because of this next part right here. We're expecting it to be 0. So therefore, within the aperture on that pause edge, we need that whole region to be 0. And if we ever had, like a little power spike or something, or if it changed too early, then in this case, we would have a hold time violation because it wasn't held for the entire width of this aperture. There we go. The most important thing, though, is just recognizing whether there is a violation. On the midterm, you got half credit if you said the wrong type of violation, which is still pretty good. So most important is just recognize that there is a violation. And you can tell that there is a violation if there is ever any sort of change that happens within your aperture, or if maybe the aperture is just sampling the wrong value entirely. So so that's probably kind of the most important thing, is just double checking that the aperture is sampling the correct value for its entire width. Yeah?
I don't remember exactly. I think I made the same mistake on the midterm where I said it was a hold-time violation. Why was it a setup-time violation?
I can pull it up. Oh, you know what? Actually, yeah, cool. Oh, nice. It's already pulled up. Sure, okay, clock to Q, there we go. So it's saying assume 2 nanosecond setup time. So 2 nanoseconds before the timing aperture starts, it says 1 nanosecond of hold time. So within this region right here, this is our aperture. So in this case, we can see that we're expecting it to be 1. And so if we look at the instantaneous moment of our setup time, is our value set up correctly? Yes, it is. Because at this moment, we can see that it is at this moment, the setup time moment, we can see that D is 1, and we are expecting it to be 1, so therefore not a setup time violation. But D changed in the middle of this region. So then what violation is this? Hold time, because it wasn't held for long enough. So this would be hold. Yeah?
So setup time is almost always that instantaneous moment. It doesn't span 2 nanoseconds.
Setup time is always this instantaneous moment. That is the definition of setup time. It is the instantaneous moment before it's like it wasn't like charged to the correct value. If anything, you could think of it as like this region before. It's like, was in this region the value correct? But really all you care about is just like this one single part. Yeah. Cool. Okay, good. So then let's just quickly do this other part now. So now it's saying assume 3 nanosecond setup time. So 1, 2, 3. Okay. Do we have a setup violation here? No, because it is set up to the correct value. Okay. 2 nanosecond hold time though, so we go 2 nanoseconds before the clock edge. Was D held constant throughout this entire aperture? Yes. Therefore, yeah, so this is no violation. Okay, now assume maybe, so new question. Assume we have, assume we have 0.5 setup and 0 hold. Okay, so really quick, so take 20 seconds, tell the person next to you, what violation will this be? Okay. So our aperture is going to start 1/2 nanosecond before the clock edge, so it starts right here. Is D set up to the correct value here? No. So this is setup violation. Is this what we got? Okay, yeah.
So quick question for setup violation, we're not just looking at like the next clock cycle, it's like any time after that, right?
The setup time is you're looking however many nanoseconds before the clock edge, and like at this time, was it charged up correctly?
How do we know what the correct charge up is?
On the Q value, the expected Q. So we're expecting here for it to be a value of 1, but if we look, we can see that D is actually a value of 0.
So we just look at the future clock cycles, any time it turns 1, then we would.
So it's this clock cycle still. So here's the clock edge. We're just like really zoomed in. Like we can imagine that it goes down to 0 next, whatever, and then there's another thing. So it's still the same clock cycle. It's a 3 nanosecond clock to Q. Yeah, so on this clock cycle, we check what the expected Q is, and then we check the setup. Okay, cool. Okay, final quiz question. Let's do, yeah. So 2 nanosecond setup, and then negative 0.5 hold. All right, this is the last question that we will do on this, and we'll move on to another topic. So take 20 seconds, chat with the person next to you. Okay, so 2 nanoseconds before this clock edge, are we set up to the correct value? Yes, we were expecting 1, we receive 1, good. But now if we go over to where the hold time ends, so here's now our aperture, was D held for the expected value for this whole period? No, cool, okay, so this is what? Hold time. Because it changed in the middle of this. Okay. All right. Cool. So in theory, now you are all experts. Yeah. Make sure you understand this. I will move on. Yeah?
Okay, just for my sake of clarity.
Yeah.
So if the value changes in the window, it's always going to be a hold time violation?
Unless there was already a setup violation.
Yeah, besides that. And then
Yeah.
you find a window that it's the setup value plus the hold value if it's positive, or you're subtracting. You're making
Right.
the window smaller if
Yeah.
the hold time is negative.
Exactly.
Okay.
Yeah. Yeah.
So there's only a single discrete opportunity to have a setup time violation.
Correct.
One.
Yeah, one single instantaneous moment. Yeah, exactly. Yeah,
And the setup time and the hold time always creates the window. It's not like.
exactly. All right. Cool. Okay. Maybe have a study session about this, chat with your friends, and become experts on setup and hold time violation. Good. So, actually, you know what? Okay. I think the question that was hardest on the midterm was this one. So let's just quickly walk through it again. So this question is, okay, cool. This question, it's a little bit complicated. So we have a counter, a 3-bit counter that counts from 0 to 5. And then when the counter equals 5, it should pause until the reset is activated. But whenever it tries to output the number 3, because whatever counts up from 0 to 5, whenever it tries to output 3, instead it should just go and output 2 instead. So that is the description of this problem. You are also given a equals to 5 and equals to 3 units, which you had to implement here. And this is how you implemented them. Hopefully this is what you got on, for your answer. But then down here, let's go and try to make a schematic that implements this. Okay, if we need a counter at all, what cells do we need? How do you make a counter? Yeah, so we have an adder, and what else? So counters in general don't really need muxes. A flip-flop, yeah, thank you. Cool, so this is kind of the most important part is we have a flip-flop, and then maybe, sure, it's taking in value from this. I don't know, yeah, something like this. And so then now we have to feed in inputs, and we could probably imagine that, so just a basic counter would have a structure like this. But the question now is like, well, we don't want to add one every single cycle. So instead, what we want to do is add one just until this now equals 5. So that's where we can utilize our equals 5 unit. So equals 5. So if we feed in now the value out of this flip-flop into this equals 5 unit, then, yeah, maybe we now can put that into a mux, as someone said. Yeah, cool. So maybe the mux goes into this input to this counter right here. Great. Okay, so now we need to decide kind of what happens. So if the number is equal to 5, then what do we probably want to add into our system if it's equal to 5? We probably don't want to add anything. We want it to freeze, so we can say add 0. If it's not equal to 5, then what do we want to add? 1. Okay. So great, so this now implements a circuit that will start at 0, probably assuming that we have maybe a reset right here. So it starts at 0 and then counts up until finally now it equals 5. So yeah, if the counter is currently at the value 5, so it will come along, propagate through, and then now it passes into this. And then here we can see it does not, or here it does equal 5, so then this will be value 1. 1 will be passed into here, and we'll take this 0 path. So now we will instead just be adding 0 to this. There we go, cool. So that is the first kind of constraint. But now the next thing is we also need to make sure that anytime it outputs 3, we actually kind of want to override that and instead output the number 2. So yeah, if whenever the counter equals 3, we should actually output 2. Okay, so if we have this counter, how do we modify this to now have the override signal? Okay, yeah?
You add another mux on the Q side of it.
Okay. So maybe, yeah, another mux. And what should maybe the selector for this mux be?
Equals 3.
Sure, yeah, okay, so this equals 3. What should the input of the equals 3 be?
The Q as well.
Okay, Q, good. So Q comes in here. And then what happens if the number is not equal to 3?
It's just the Q output.
Okay, good, yeah. So that means just output like normal. If the count is currently at 3, output like normal. If the count is equal to 3, then what do we do? Output 2, thank you. Cool. There we go. So this is a very reasonable implementation here. Uses the equals 5, uses the equals 3, as was specified here. You have 2 input muxes here and here. And then you have your flip-flop. Yeah?
Do we need to label data buses?
No, you could. Yeah, maybe. Up to you. If you feel like it will improve your diagram. Sure, so we can do it in this case. So it says that it is a 3-bit adder. So yeah, so we could probably go and label all these. So we could call this 3 bits. This is 3 bits, 3 bits, 3 bits, 3 bits, 3 bits. And then this comes through. This is 3 bits, 3 bits. This equals to 5. How wide is this? This is only 1 bit. What about this equals to 3? What is this? This is 1 bit. Here, this is 3 bits. Yeah, so we could do that. For me, I don't know, I feel like it clutters it up just a little bit. As long as it's correct, as long as your schematic is correct, I think it's fine to leave off the bus labels. Yeah, more of like a visual preference thing. Yeah, sure. Okay, only I think about, I don't remember the exact number. I think like 40% of the class got this question correct, maybe less. So, I'm assuming that all of you, since you're here, you're engaged, you probably got this question right. And I'm sure, your friend who's still sleeping in, even though it's 10 a.m., maybe, give him a little jab in the gut, be like, hey, that question you missed on the midterm, you should really study this. We went over the answer and tutor them. Okay, yeah.
So where is that possible? Where did it go back? Or does it not go back?
Say it again. So.
Does it not go back to a
This right here.
Is it just a option?
So the flip-flop is just storing the counter. It's just counting from 0 to 5, and we probably don't want to take this. Because if we took this value and passed this back into the flip-flop instead of like this, like if we got rid of this, that would mean now that we would probably start from like 0 to 2 and then maybe freeze on 2 or something. Like we wouldn't keep counting up. We need some way to like store whatever state that our machine is in. And even though our output is 2 for 2 unique states, it's outputting 2 when we're in like the 2 state and also the 3 state. We need to make sure that our like output logic is completely separate from what the current state is that we're storing in our flip-flop. So we don't want to pass this in because most likely it will just break things. You would need like another flip-flop to keep track of like which 2 you're currently on. Like, are you on the first 2 or are you on the second 2? And okay. So because of that, it's best to just have like your own separate circuit just for keeping the state and another separate circuit for driving the output. Okay, cool. I have another example that I prepared. We'll see how far we get into it, but so this is the question. This is a totally reasonable question to be asked on the final. It's joining together a lot of different concepts. So it says design a circuit that receives a UART signal that is 8 bits. And then the question is now like drive these outputs correctly according to these inputs. So we're going to spend the last 24 minutes of class working on this question. So UART. This is just like one single wire. It's just this RX wire, and it's just, it's a serial. And so what can anyone explain to me what the UART signal should kind of look like in this case? Yeah?
Should have 7 data bits and 1 parity bit.
Sure. Maybe in this case, we just assume no parity bit. Parity. Okay, so good. But before that, before we send the bits, what else do we have? Okay. Yeah.
And then like the start bit.
Yeah. Right. So if this is RX, D, then so first, so it's held high, right? And then the start bit is denoted as what? Is it a 1 or a 0? 0. Okay, so a start bit will be sent, and then after that, then we receive the 8 data bits. So 8 data bits. And then after that, then what will the output be? 1s, yeah. And this would be like the stop bit. Okay. this. Okay. So, okay. Starting out this question, what is probably the first reaction that you should have in that, like, what is the first step in doing this? Yeah?
Maybe the start bit?
Start bit, okay. So when designing the circuit, like what's the first like thing that we maybe put down? Sure, okay, so we're probably going to have a flip-flop that is keeping track of what? States, yes. So actually, maybe before we even start drawing a circuit, instead we should start thinking about this not necessarily as a circuit, but as a what? State machine, okay. And when you go and decide to make a state machine, what is the first state that you should always start with? Idle. So that is your first step. Immediately, whenever you see a question that's like this, it's like, whoa, like I have to do a bunch of things. I need to account for the start bit. I have to account for data bits. I have to like worry about all this. The first thing that you should do, just get some sort of foothold, is just draw a little circle and call it idle. Okay, great. So now we have this. So now the question is, well, how do we get out of idle? Okay, how do we get out of idle? Yeah, we receive a 0 on the RxD. So if we receive a 0, that means that we've received the start bit. And then maybe after this, we go to another state. And what probably would our next state be after we've received start? Anyone? Can't. I don't know. Maybe like receiving, right? Because it's receiving all of the data bits. That's probably what I would call it. Sorry. Receive, whatever. Receiving, okay. Good. So we're receiving, and yeah, this is based off of RxD equals 0. Okay, so now we're receiving. How do we know when to exit receiving? Well, remember, so there is this stop bit. And stop bit, whenever it goes 1, that denotes that it's stopped. But I don't think we can really use that, right? Because we could potentially receive like 1s in our data bits. So how do we make sure that we've received all of our data bits? Yeah?
We just gotta count how many bits we read, so it'll be easy.
Yeah, exactly. So what we do is we just have probably another separate counter. So, okay, great. So now here's our real like first bit of circuit that we're drawing. So maybe first, so we put down this flip-flop that is like some sort of counter. And then, we have like some sort of counter thing. I trust you all to design a counter that maybe counts from 0 to 7 or something, 0 to 8, and then outputs 1 with that. Very similar to the midterm question. But I guess we could quickly kind of make one right now. So just have like adder, and then maybe, an equals to 8 unit that feeds into a mux. So equals 8. So we say if it's equal to 8, maybe add 0, not equals to 8, add 1. I don't know, something like this. So this will now add 8 until it equals, it'll keep adding until it equals 8. And then now inside of this receive, we exit receive. Maybe go back to idle. When? I don't think it's a trick question. It's just when. What was that? Yeah, exactly. When the count is equal to 8. So when the count equals 8, that probably means that we've received all of our data, and now we can go back to idle. So there we go. So count. And if I were to put an underscore here to like say like the output of the flip-flop, what should I put here? Q, yeah, so to get like the output of a flip-flop, you can just put like underscore Q. And this is very clear to me, like, okay, so count Q, this is very clearly coming out of this flip-flop. Okay, great. And then, yeah, maybe we also are keeping track of all this data inside of a shift register. Remember shift registers? So maybe we can kind of like shift in the data as we go. So shift register, that is when you have a bunch of muxes feeding flip-flops. Okay, maybe we have like 8 of these all in a row. And well, at what point do we want to be shifting in data, and when do we not want to be shifting in data? If we look at our state machine. Yeah, so maybe when we're receiving data, maybe that's when we shift in things. And maybe so this input right here, maybe this is RxD, so this is the input from our like receive signal. And so now we're shifting in the data, and so now each of these go up here. So we say maybe when we are in the receiving state, so this input will be like equals receive. And state Q will probably be passed into this. So when state Q equals receive, then in this case, we shift over everything. When it does not equal receive, then maybe we keep the value that it's already at. And imagine that this continues for maybe 8 whole entries. It's not just these 3. It's like 8 in a row. We have this like repeated structure right here. So whenever state Q equals receive, maybe we just start shifting in all of the Rx data. And then by the time that now count equals 8, then now we have fully shifted in all of our data. And once we've shifted in all of our data, that denotes that we can maybe go back to idle. Okay, yeah, so absorb this for about 1 minute. Go and explain to the person next to you what just happened. See if you can understand exactly like why we needed this state machine, why we need this counter, and why we need this shift register. And go and explain to the person next to you what the purpose is of each one of these 3 units. All right, take 1 minute and get some discussion. All right, cool. So I think we might have an off by 1 error here, I will say. I think maybe instead of equals 8, maybe it should be like equals 7 or something. I won't bore you with trying to solve this like off by 1 error. In theory, you would just plug this into Verilog, like you'd implement this in Verilog, and then you would see just easily in the simulation, it's like, oh, like I just need to like change this one thing. It's a little bit hard to like run a simulation just like on paper. So yeah, so we'll just kind of pretend now that this implementation kind of fully works. Does anyone have any questions? Like, were you discussing with your partner? It's like, wait a minute, like this doesn't make any sense. Anything? Like, yeah.
It's just a sanity check. If there was a parity bit,
Yeah.
how would we just modify our count key value in this situation, or would we do something else?
Personally, I would not create another state. I would probably just read in the parity bit, and then in a next like step, I would just Or like when I go to output the data, maybe I would just output like this last kind of register right here. I would output this as, or I guess actually, I would output this as the parity bit, and then I would output this as the data bits. So that's what I would do, is I would just, on like not even a part of the state, I would just, inside of the outputs, I would be like, here's the parity bit, here's the data bits. Yeah. Okay. Cool. Okay. Good. Oh yeah.
In this case, would output valid just be tied to equals idle in the same machine?
Oh, great question. So actually, the next thing I was going to talk about was the ready valid interface that is on this, because yeah, there is one thing that we are missing, and it is this out ready and out valid. Notice that out ready is on the input. What does out ready mean here? Anyone?
Ready to take a value.
What was that?
You're ready to take a value.
Who's ready? So it's actually not related to like this circuit. It's instead who. So this, we're receiving as an input this out ready signal. So this would maybe be like the output from maybe an adder or something that we are plugging into. So maybe like from UART, like we are trying to send this data bits, like all these data bits, where we're converting all of these serial bits into one single parallel bus. Sorry, just checking the time. Okay, good. So yeah, we convert the serial bits into one single parallel bus, and then we want to maybe send that out to another module with a ready valid interface. And so that other module, maybe that has some sort of like delay or stalling logic or something. Maybe it for a while won't be ready to receive certain data. So that is the purpose of this out ready, is is the thing that we're trying to send it to, is that thing ready? And so if this out ready is false, like if it's 0, that means that we need to now wait. Like we can't just send out that data immediately, because the thing that we're sending it to wasn't ready to receive it. So actually, we are not quite done with this because we have this out ready input. We now need to account for this and make sure that our circuit doesn't move on too quick, because we need to make sure that we are outputting the correct value until finally the thing that we're sending it to is ready to receive this output. Okay, so instead of just moving straight to idle after receive, maybe instead we should check this out ready. So we can say, so while our shift register is full, so while count Q is equal to 8, so while we've received all of the data, and also out is ready, then in that case, then we can move to idle, because we were in fact able to send out that data. So we can have this situation right here. Come on. No. Okay. Good. So while out ready and this, then we can go back to idle. But what if out ready is not true? Then what happens? Well, we can't stay inside of receive because we've already received all the data. We don't want to keep shifting over this data. We don't want to keep shifting in data into this shift register, because that will corrupt things. So we want to definitely move out of this receive state. And so what state would we probably want to call it if we're waiting for this out ready to become 1, to become high? What do we call it?
Waiting.
Sure, waiting for ready. Yeah, I think that's a great name. Oh, okay. So I'm getting a phone call. Okay, cool. Yeah, so maybe here we have waiting for ready. Wait for ready. And so here, this is the same thing where where count Q equals 8, but now instead of ready, now ready is 0. Put an exclamation point. Okay, so out ready is false, but the count is done. So now we are in wait for ready. And so at what point do we move out of this wait for ready state? What was that? Yeah, and then finally we can move out when out ready is 1. And now we don't need to check for count anymore because we already checked it on like the previous transition. Okay, so now I guess the final output is this out valid right here. So now we need to drive, we need to drive this out valid. So the question is, how do we drive this out valid according to the state machine? In other words, like when is our output, when is our output valid? What was it? So it's not necessarily an idle because the whole idea is that when out is ready, that is when data flow should occur. So after we've already sent the data, we actually want to reset valid back to 0. Yeah, so it's when out ready is 1, but then also it's when like count Q is probably equal to 8. So when count Q equals to 8, that means that our shift register is currently like filled up. It's currently good. So when actually I would say the most important thing, is out valid is when count Q equals 8. But then maybe also we can say it's like maybe we can also, when we transition back to idle, now we reset the counter. So there's maybe like 2 things happening here. So I'll add in another thing right here. So we can say, for this counter, so that reset is when maybe like state D, meaning like the next state. So when the next state is going to be equal to idle, then now we are going to reset. But then also we can drive out valid whenever this equals to 8. And with this, we've now kind of completed the question. I guess maybe we should convert this into a circuit as well, but we could probably do this. We could just make a big mux tree and make maybe like a flip-flop that is fed by a big mux that has an idle state, receive state, wait for ready state. And then we could draw out this kind of big mux tree and then also take in each of these kind of these situations right here. But the main functionality is all included in just this circuit right here. So here's our state machine, and then here is our shift register, which converts the serial port into a parallel port. And then here we have the counter that keeps track of how many bits inside of our shift register we've actually used. So there you go. Reasonable final question? Maybe it doesn't look too bad now that we've gone through it. Okay. Yeah. Oh, for data, you're saying?
No, the alt value.
Out valid? Out valid? So out valid is being driven by the counter.
Yeah.
So this is just an output. Yeah. So this is where it's driven, and it would be just passed as our output of our module. Okay. Any other questions? Okay. Cool. Good. Oh, yes.
This is nitpicky, but couldn't you, instead of using the other equal 8 module, couldn't you just use the input to the adder? Because
You say, oh, yes. Good. Yep. Cool. Okay. I will see you all on Friday for our final class. Please post any questions that you have to the Piazza post so that I can make sure that you are all as prepared for anything that you need preparation on. Okay, thank you.